Section 14.8, Jacobians. This is the last section in this chapter and in this class. In this section we will see how we can make changes of variables, and it will explain why when we were, for example, changing from rectangular coordinates to polar coordinates, we had this r that we had to multiply when we changed dx dy to r dr d theta. And first, I want to introduce the case with a single variable where we may notice that actually Jacobians are not completely new. When we made u substitutions in just one integrals, we also had to manage stuff in a way that is actually the Jacobian. So if we look at this example here, we're not going to compute that, but if we want to integrate sine x dx, obviously we could do that, but just for the sake of an example, if we decided to make a change of variable and then call x arcsine of u, then our variable would become u. So this is, if I substitute x as arcsine of u, sine of arcsine of u is u, but we also have to change dx. And if you remember, dx is equal to the derivative of arcsine of u times du. So this is where this thing would pop up when actually sine x substituted just becomes u, but dx becomes arcsine u prime, which is 1 over the square root of 1 minus u squared times du. So this part here would be the Jacobian in one dimension. When we have a double integral, the way to calculate what the Jacobian will be is shown here. So we need to find partial derivatives for each of the variables in terms of each of the other variables that we are changing for. And this, you might recognize it as a determinant for 2x2 matrices. So it's this action that we will do countless times in semester 2. We kind of multiply across and then we subtract and multiply across again. So partial x partial u times partial y partial v minus partial y partial u partial x partial v. We have to take the absolute value, but the Jacobian itself is only the determinant without the absolute value. So this is what we can do, and then if we were making changes of variable in 3 dimensions, then it would just be determinant of a 3x3 matrix. So with this in mind, we may want to look back at the change of variable from rectangular to polar and see whether it matches what we had learned, which is that if we change dx dy to dr d theta, it actually becomes r dr d theta. So let's see if the Jacobian is actually equal to r. As we know, x equals r cosine theta and y equals r sine theta, so partial x partial r, partial x partial theta, partial y partial r, partial y partial theta gives us all these partial derivatives, and then if I apply the Jacobian, it becomes cosine theta times r cosine theta minus sine theta times negative r sine theta, which becomes something where we can factor out r, and in the parenthesis we have cosine squared theta plus sine squared theta, and therefore it is indeed equal to r. So here's an example, because until now we had never really used changes of variables except for these custom changes from rectangular to polar or to cylindrical or to spherical. So in some situations we may want to make a change of variable. It makes our life a lot easier. For instance, if we are given a region like this, which is diamond shaped, but notice that this intersection here is not aligned with that intersection here, we could technically integrate over this region, but it would be very painful. We would have to integrate from here until here, and then integrate from here until there, and finally integrate on the last region. So we would have to split R into 3 subregions and integrate on each of them separately. The reason is we can integrate from this to there, but then the bottom function changes, and then eventually the top function changes. So there's three different subregions that we would have to create. Much better if we can find a change of variable. And if we pay attention to how the region is defined, x minus 2y equals 0, x minus 2y equals -4, we notice that we could make a decision to make the change of variable u, or here v, equals x minus 2y. That would help us a lot, because now our limits would be v equals 0 and v equals -4. Likewise, since we have x plus y equals 4 and x plus y equals 1, we can substitute u equals x plus y, and that would become u ranges from 1 to 4. So with this idea, our region would now become a rectangle in the UV plane. It would be a very simple region. It would be a rectangle that sits nicely aligned with the U and V axes. So if u equals x plus y and v equals x minus 2y, we have to solve these for x and y, because what we need is partial x, partial u, partial x, partial v, and so on. So with a little manipulation, we can reach the fact that x equals 2u plus v over 3 and y equals u minus v over 3. So it's easy from here to figure out what partial x, partial u is. It's just 2/3, and so on for all of these partial derivatives. So the Jacobian is equal to this, and it ends up being equal to -1 over 3. So keep in mind that when we put the Jacobian into a double integral by changing the variable, we want the absolute value here, so it's going to become +1 over 3. And we have to make sure that we change the limits of integration. So v ranged from -4 to 0, and u ranged from 1 to 4. But this is an easy integral in this situation that we can just follow step by step very easily, and in the end we get 164 over 9. So yeah, I never talked about the fact that we were integrating 3xy over that region, which explained why we have 3xy here. That's it for this section and for the entire chapter. Thank you.